Welcome. In this video, I wanted to talk about this problem as an example of how to solve problems, in particular applying Newton's second law. Although I've had videos relating to this, I thought it would be fitting to have another one because of what I noticed recently. It seems people are not reading the questions properly, and as a result, there's a lot of details that they skip over, and that eventually comes back to bite. So the first thing, what I would like you to do whenever it comes to solving problems, this is very, very important, and it's deeply fundamental, is the first thing, please don't miss this. The first thing is, please calm down. You have to calm down and read the question properly. Whenever you panic, you're going to miss out on data, and you're not going to read the question properly because some of the hints on how to solve the problem are actually embedded in the wording of the question. So, number one, please calm down and make sure you read the question thoroughly. I would recommend you read it at least more than 3 times. Do not jump ahead and look at the values and look at this part of the question. Please don't go to where there's a question mark. Students have this tendency of jetting all the way to the end and figuring out, looking at this and looking at the diagram. Let's just read the question as is and then see what we could do with the info given to us. Okay. So in figure 6-3023, we're told that a sled, okay, we don't have this figure, but I'm pretty confident we have enough data to recover the picture. A sled is held on an inclined plane by a cord pulling directly up the plane. Okay, so this first sentence allows us to draw something. This allows us to form a picture. So I'm going to go ahead and draw a picture. So I'm going to say, here's my inclined plane, and here's my sled, and my sled is going to be a box like that. And I'm told that the sled is held on an inclined plane. So this suggests to me that there's no motion here. So the sled is held at this point. So it's held by a force or by pulling up directly on the plane. So here's our force that's going to hold up the sled. Let's call it F sub A. And we're told that the plane on which the sled rests is inclined. So I can preemptively introduce an angle here because we're told that it's resting on an inclined plane. So I expect for there to be an angle of inclination. So that's what I've harvested from the first line. Now we go further up, further on in the question. We're told that the sled is to be on the verge of moving up the plane. Okay, the sled is to be on the verge of moving up the plane. So we want to hold the sled by applying such a force, such that if we were to increase this force by a small amount, even by a fraction of a Newton, this thing will begin to move up. This, therefore, will begin to inform me of something, that if we're on the verge of moving, this kind of gives me an idea of if there's friction, what kind to expect. Actually, put it on the comments right now and tell me what kind of friction do you expect for there to exist if we're to be on the verge of moving. So I'll leave that over to you. Okay, so we're going to be on the verge of moving. So there's going to be some kind of friction. Type it in the comments and let me know what kind of friction would that be. You could pause the video over here and put in your response. Okay. And then they tell us that in figure 6-28, which is this one, this is the graph, we're told the figure captures the magnitude of the force required on the cord in order to keep the status of maintaining the sled on the verge of moving up. Okay, so the force that's required is plotted over here. Notice on this plot, it's quite unique. Maybe let me continue with the question. So the force required of the chord's force, F, the magnitude F required of the chord's force on the sled is plotted versus the range of values for the coefficient of static friction. If you paid attention to this question, notice they've already instructed you of what kind of friction there's going to be. If you've typed on the comments, if you've typed kinetic friction, this would instruct you otherwise, that the kind of friction we're going to be involved with is going to be the static type. Okay. So the plot here represents the amount of force we need to apply when the roughness of the incline is given by this. And by roughness, I mean the coefficient of static friction. Remember, that's what the static coefficient of the coefficient of friction measures. It measures the ease with which the object can slide over a surface. So the fact that here there's an increasing mu s here tells us that the roughness is increasing, hence it's more difficult for the object or the sled to slide over said incline. Okay, now if let's take for example, if the object, if the smoothness or the roughness of the incline was 0, that is mu s, if mu s was 0, according to this, the force we would need to hold the sled on this point, on this position, would be equal to F1. This is what the graph is telling us. So if we had a very, very smooth surface, oh, by the way, I should say, the fact that mu s is changing means the incline is variable. We can change the roughness or smoothness of the incline. It's very easy to change the smoothness of an incline. You could pour water, that will reduce ms. If you scratch it up, you make it rough, then you could increase mu s. So my point is, it should be noted that the incline has, it's easy for us to change the roughness of that incline. Okay, so let's read off what the graph says. According to the graph, when mu s is equals to 0, let's say when mu s is equals to 0, the force Fa we need to apply is going to be equals to 2.0 newtons. That's what this is telling us. And another key point that they give us, another good label they give us, is that mu is equals to mu 2. They tell us that when mu s is equals to 0.5, according to the graph, the force we need to apply in order to keep the sled from moving down, or rather to be on the verge of moving up, the force we need to apply, Fa, is going to be equals to, that's 5.0 newtons. So this is all the information we've just harvested, and now let's see. It should be noted that what are we not changing according to this question? What we are not changing is the sled. It's the same sled. We're not changing the sled. Also, we're not changing the incline. That is the angle of inclination. We're changing the roughness of the incline because mu s is changing according to this plot. And when we change the roughness, we see that the force also changes. But what we are not changing is the sled, which means the mass of the sled is going to be fixed, unchanged. And also, theta, the angle of inclination, is also going to be fixed. Which means we can use this information. Maybe let me put it another way. Theta, the angle of inclination for this situation, is going to be the same as the angle of inclination for that situation. This means we have two incidences or instances where which we can use to determine the angle which we're looking for. Actually, the angle, what we're looking for in this question is theta, 0. Oh, sorry, theta. Okay, so then now we've kind of dismantled the problem, and essentially we've recovered the picture. Although here we're supposed to look at the picture, I suppose it's in the book, but if you don't have the book, it's unnecessary to look for it because we have essentially recovered it. Now we need to consider, what do we have at our disposal to use? There's friction here, so it's time to put down our tools. What do we have available? Since there's friction, we know there's going to be the static type, and that means the maximum static friction. One of the tools we have available to us is that the maximum static friction is given by this. And moreover, since the sled is to be held at to be on the verge of moving, that means our acceleration it must be equal to 0. This is just, I'm harvesting the data from what the question has given me. And moreover, I think, one more thing that we have available, which is always true, at least for speeds less than the speed of light, we know that the net force must be equals to the mass of the object times the acceleration. So this is what we have. So let's see how we can use this. Again, I would like to encourage you, stay calm and approach the problem methodically. So this is what we have. Let's go and see how we can use this. I'm going to redraw the picture. So this was just to show you how to analyze a problem. Analysis. This is the analysis part. And I have to warn you that this is long because I'm trying to demonstrate. When you do this, when you're doing an actual problem, maybe for a test purpose, you might not take the same amount of time I'm doing, but yeah. Okay, so now let's actually solve the problem. What I always encourage students to do is, whether the question requires it of you or not, whenever you're dealing with forces, it is always wise to draw a free body diagram. So suppose this is our sled, and suppose this were the incline, and shortly I'm going to delete the incline. What forces are present? Well, because the sled has mass and we live on planet Earth, we know there's going to be the force of gravity. There's going to be the force of gravity pulling the sled toward the center of the Earth. And there's the force we need to apply to keep the sled on the incline from the verge of sliding down. There's our force. I'm going to call it FA. And because the sled is resting on the incline, I know that by Newton's third law, the surface or the incline will react and apply a force upward to support the sled. That force we have a fancy name for. We call it the normal force. So there's our normal force. But remember, the sled is supposed to be held in position so that it's on the verge of moving up. So if the tendency of the sled, or the sled is on the verge of moving up, and we have friction on the surface, we need to, I think it should be clear that friction is going to be pulling the sled down. So I change color to signify the frictional force. And because we are on the verge of moving up, that means we have reached the maximum possible friction here. The maximum possible static friction, I should say. So these are the forces that are acting on our sled. So let's return to the red pen. Now we return to the red pen. Now it's time to delete our incline. Now that we have identified all the forces acting on this sled, it's time to choose a coordinate system. And a coordinate system is very critical because it will help you figure out what forces have you taken into account and which ones have you not. So over here, I'm going to draw a dotted line to signify the angle of inclination. That's going to be over there. So in this problem, I would choose the angle of, the coordinate system in this fashion. I would choose this. So the green coordinate system signifies my choice. That is, anything up the incline will be regarded as positive, and anything that's perpendicular in that direction will be regarded as positive y. So then, now we're in a very good position to apply Newton's laws. Newton's law says, notice over here I quoted them in a vectorial form. That is, the net force in vectorial form, that is in 3 dimensions, is going to be equal to the mass times the acceleration in 3 dimensions. This equation is true in each individual direction. That is, there's a version of this equation that's true in the x, there's a version of it that's true in the y direction, and there's a version of it that's true in the z direction. So since here we have a 2-dimensional problem, we know that this will be applicable both in the x and in the y. Okay, so let's go ahead and apply Newton's second law. Let's start off with the y direction. Let's start off with the y direction here. The y direction tells us that the normal force, let's go back. It's going to say that the normal force minus the y component of the force of gravity. The y component here will be resolved by using the cosine function. So this will be Fg cosine of theta. This will be equals to m times ay. But notice, we are not interested in having the sled lift off the surface. We don't want the sled to fly off the surface. Neither do we want it to dig and excavate the ground. So what can we say about our acceleration in the y direction? That has to be 0. This enables us to find that the normal force is going to be equals to Fg cosine of theta. Remember, don't lose track of the goal. The goal is we're looking for theta. But right now I'm applying Newton's law in order to figure out what's, we're using Newton's law to navigate to this goal. Maybe let me put it that way. Now let's apply Newton's law in the x direction this time. In the x direction, things are a little more interesting because we have this force Fa in the x direction, and we have this force, that's a frictional force, in the x direction, and the force of gravity has an x component. Let's go ahead and apply Newton's second law. This is going to look like minus Fs max. The reason why I pre-supply a minus is because I've designated that everything every force acting up the incline should be assigned a positive. So friction has a negative, or it's acting down the incline, so that has to be assigned a negative. The same goes for the x component of gravity. That's going to be Fg sine theta. This is this component. This side serves to be the opposite of that triangle, or it's opposite to that angle. And then there's going to be finally our third force is going to be Fa. Fa is equals to m times acceleration in the x direction. But remember, we're on the verge of moving. We're not moving yet. What can we conclude? Since we're not moving yet, this means our acceleration in the x direction will also be 0. Okay, that's great. Now, let's unpack what this means. Remember our data? Our data, we knew how to determine this from our previous data. So we gotta unpack what this means. According to the information we have, this is Fs max. So we could substitute that in there. So we're going to end up with minus mu s times Fn minus Fg sine theta. This is going to be plus Fa. This is going to be equal to 0. Now, Fn we've already resolved. You still remember? We have already found what Fn was. Fn was determined there. So we could go ahead and substitute Fn in there. If we were to do so, we would find that Fn is going to be, well, this equation is going to be given by mu s times Fg cos theta minus Fg sine theta plus Fa. This is equal to 0. Now we have an equation which is very interesting. It contains the things we are looking for. It contains theta. We are looking for theta. So this equation contains the theta we're looking for. But it contains unknowns also. It contains a couple of unknowns. The first one is mu s. We don't know it definitely, but actually it's quite interesting. We can read it off the plot. It also has Fa, which we don't have, but conveniently we can read it off the plot. And in particular, we can use this fact. We knew that when mu s was 0, we knew what Fa was. And we also know what Fa is when mu s is 0.5. So we can use these two data sets and substitute them in this equation. We're going to end up with two equations. And when we do so, we're going to find something cool. Let's quickly do that. When mu s is equals to 0, so I'm going to write it down just for clarity. When mu s is equals to 0, Fa is equals to 2.0, which means this equation, I'm going to call it equation A, which means equation A takes the form that this is going to be minus Fg sine theta plus 2 is equals to 0. So now we have one equation, let's call it 1. And if we were to do the exact same thing, let me copy this equation for the new page. I'm going to have to go to a new page because I didn't take care of my real estate properly. Okay, so the other instance we know of is that when mu s is equals to 0.5, Fa is equals to, 5.0. It's 5.0 newtons. Now let's substitute this piece or this data set into that equation. Well, this tells us that, let's say from equation A, what we learn is that minus 0.5 Fg cos theta minus Fg sine theta plus 5.0, this is going to be equals to 0. This is equation, let's call it 2. So now notice we have two equations. We have two equations which we can use to solve. I'm sorry, let me back up. We have two equations, equation 1 and equation 2. We have two unknowns. What are our unknowns here? It's Fg and theta. But we can use this equation to find what Fg is going to be. Let's go ahead. Let's say from 1 we know that Fg is going to be equals to 2 divided by sine theta. Now, if we take Fg, this what we found of Fg here, and substitute it into equation 1, let's call this equation 3, then substitute equation 3 into equation 2. This will hopefully convince you okay, I don't want to, the rest of this is kind of pretty much algebra, but the whole point of this video was to try to convince you that you always have enough tools The question provides you with as much detail as you need. And in class, we have presented to you all the details you need to solve these kinds of problems. So if you, number one, stayed calm, number two, read the question properly, you have all the tools you need to solve this. Okay. Actually, I will leave this. I'll leave this for you. Maybe if you want, you could post on the comment section, what do you find the angle? What is theta? That is, substitute this equation here into here and tell me what do you get for your angle theta. And then I'll respond whether you're correct or not. I will respond, but right now I'll leave it to you as your exercise. But the key here is, number one, you have to keep calm. Panicking will not assist the situation. You have enough tools to solve these problems. Number two, you have to read the question thoroughly. I would recommend reading the question at least 3 times. And at the end, always check, have I responded to what the question asked me? So obviously, I'm stopping at a point where I haven't responded to the question, but I leave that over to you. What do you find theta to be? Okay, this video is already too long. I better stop it here. I look forward to your responses. All righty.